Alrighty, hello everyone, and welcome to Dynamics. So, for this week, basically what we did was the first lecture was just kind of getting an idea of what the course structure was, and then that was only like 30 minutes or so, and then we only had one proper lecture. So I imagine this one's going to be the shortest out of all of them, all the weekly updates. Actually, I can't guarantee that because currently we are about to experience a lot of snow, and I have I have a class from 5 till 7:30, and the university's supposedly going to close at 7, so I'm not really sure how that's going to work, but either way, we will see what happens. So this may be the shortest video of the week, this may not be, but either way, this is the beginning, so section 12.1 and point 2. Point 1 is really just the introduction, so we kind of like gloss over that. And then 12.2 is rectilinear kinematics, focusing on the continuous motion. So when talking about dynamics, for the most part, we're going to be talking about in particles. And so when we're talking about a particle, the assumption is usually made so that you can negate the size and the shape. So we're only worried about this one mass. We do this in order to like simplify the calculations, so we don't have to worry about the exact geometry and such. So we just a single point that has a mass. So when looking at dynamics, this is that overview that I was kind of talking about. So when looking at dynamics, it breaks off into kinematics, which is like the geometric aspect of motion, where you travel and the path you travel, kind of. And where kinetics focuses on the forces that cause motion to happen. So let's get right into rectilinear continuous motion. And so this is going to be very, very basic overview. This is like high school overview pretty much. So for continuous motion, the particle travels along a straight line defined in a coordinate axis S. And all this is going to be relative to some origin point O. So the position is defined by either a vector, which is R with the little hat on it to signify it's a vector. And the thing that's going to be kind of annoying with this, R is kind of interchangeable with S. It's kind of been a bit of back and forth. Like it's not really clear which one they want. It changes a bit. But either way, you will know for sure if it is a vector if I put one of the arrows on it over top. So the vector is going to be an R or an S with hat, or the scalar, which is an S with no hat. I say a hat, but it should be more of an arrow. So the units for this is going to be in meters or feet. We're going to be using both SI and imperial. It's going to kind of go back and forth in this class. So displacement is the change in overall position as opposed to the total distance traveled. So you could have some big elaborate path that you kind of go back and forth on yourself, and then you end up at one point. So when we're looking at displacement, the only thing that we pay attention to is where you are relative to that initial point. And when it comes to distance traveled, that's when you pass through all that entire path that you've been through for ST. So yeah, when we look at the change in displacement, we subtract the final position from the initial position. That's both for whether or not it's a vector or a scalar. So I don't think I've said it yet, but okay, I say it right here. So the velocity is going to be the rate of change of a particle's position. So a vector is a quantity. The vector quantity is a magnitude and direction. So it has a value of whatever units in direction, some direction. For the most part, like when it comes to rectilinear, we're just going to assume that right is the positive direction and then left is going to be a negative direction. So yeah. So units for velocity are going to be in meters per second or feet per second. So the magnitude, just the magnitude, when we take away the direction, so the scalar value is going to be speed. So when we look at average velocity, it's going to be the change in time, not change in time, the change in position or displacement over the change in time, as opposed to speed. This is the notation that it'll make. So the velocity, the speed, which clearly lines that it is a scalar value. So it's the total distance traveled over the change in time. Instantaneous velocity is the derivative of the the position vector. And then speed is just dr over dt. So now we get into acceleration. Acceleration is the rate of change of velocity measured in meters per second or feet per second. Instantaneous velocity is found by taking the derivative of, instantaneous acceleration is going to be the derivative of velocity, or the second derivative of the position vector. And so when we're deriving the equations, we discover this. So we have, I believe that you originally start with v dt equals ds. So when you divide by that, you get ds over v. And then a dt equals dv. You divide both sides by a. So both of them end up equaling dt, which means you can set both of these equations equal to each other. Then you rearrange, you get a times ds is equal to v times dv. That will likely be helpful later on. And so one thing that we kind of think about is getting from position to velocity to acceleration and kind of back and forth. So if you want to get to position, you differentiate the position to get the velocity and the acceleration. So v equals the derivative of speed, not speed, position. The acceleration is the derivative of velocity, as said before, or the second derivative of position, or velocity times the change in velocity. So when you're looking to get acceleration you integrate acceleration to get either velocity or position. So these are the equations you're going to use. I'm not really going to explain them. Fairly self-explanatory. And then the next thing we come to is the constant acceleration. This is kind of the whole focus of 12.2. So the idea that acceleration is going to be constant, and then when we take these integrations, we end up getting our kinematic equations. So if you take the integration of the change in velocity from the initial to a final velocity, it is equal to the acceleration, which is constant, over the change of time from t naught to t, and that ends up giving us v equals v naught plus at. So the next one we get, so these don't actually correlate to each individual one. I just kind of spread it out because it looked nicer. So constant acceleration gives us the kinematics equations, again, restating acceleration is equal to constant. Often the acceleration is going to be equal to gravity. For meters per second squared, it's something you know very well, it's 9.81. However, sometimes we're going to be using metric, and so it's going to be 32.2 feet per second squared. I did have a point there, it's just not that clear. So the second equation is going to be integrating the change in position from s naught to s, and integrating the velocity from 0 to t seconds, and that's going to give us s equals s naught plus v naught times t plus half of a t squared, and that's that kind of parabolic equation that we often see. And the last one is going to be the integral of v times dv from v naught to v, and then the acceleration times ds from s naught to s, which gives us v squared equals v naught squared plus 2a times the change in positions. That can be s minus s naught. That's another way of writing that as well. But yeah, so very quick one, short 10-minute one there, and that's pretty much it for the first week. Again, just one lecture of material, and I will see you guys probably tomorrow. I don't know what I'm going to have for electric circuits. Electric circuits will be next. That's going to be posted tomorrow because I still have the lecture late tonight. And yeah, I think going forward, I imagine most of these will be posted on Saturday. If I'm on top of things, maybe I'll get it done on Friday, but we'll have to see. Anyways, hope you guys enjoyed, and I'll see you guys next time.